Well, that's cohomology. That's where the theory of cohomology came from. It's actually from the end of calculus, believe it or not.
Right.
Well, there's some of the answers that they posted in the last homework assignment, and I just think they're kind of funny. I hope your teacher responds.
So when I got the pass and I thought I was turning it on,
I'm not sure which one he's talking about.
Oh, the motor. Okay, yeah.
I noticed 20 minutes into it, so after 20 minutes, it's okay, but it's a boring first 20 minutes for the lecture.
Well,
You see that corner of the board.
Oh.
You can hear it though.
Yeah, you could hear it.
You're like, what is he writing?
Yeah.
I mean, you post your notes on there so they can pretty much see what you were writing. But yeah, that sucks.
Okay. So let's, where were we? We were talking about
Closure.
closure, rank. See where my notes are.
Really with, I think, the closure property.
So last time I defined rank for you and I showed you some properties of rank. Then I defined closure for you and I stated some properties of closure, which I didn't prove. So I plan to prove these things today. And before doing that, I want to show you a couple of small lemmas on rank and closure that are going to be useful for us. I think these lemmas are going to make a lot of sense to you. But we're only learning what these notions of rank and closure mean, so everything has to be proved at this point. So here's an easy lemma. Let's say that you have a matroid, you have a subset of the ground set, and you have an element of the ground set. Then what can you tell me about the rank of the set plus the element? Well, the idea, of course, is that if the set had rank x, then by adding one element, you either leave the rank alone or you increase it by one. I think that makes sense. But we don't know that it's true yet. So let's prove it. Question?
Isn't this part of the homework?
Homework. This is part. This is part of the homework.
No, kidding.
This is one of the things you have to prove in the homework. So I don't have to prove it. It's homework. Thank you.
Sorry, you really understand.
Sure, I'm the only one thanking you right now.
I was like, oh good, I can see if I was right.
Anyway, this is the easier part of that exercise. So that's one lemma. Is that by adding one element, you can only increase rank by one element. And the second lemma is about the interaction between rank and closure. And it's another lemma that I think is going to make very good sense to you. Which is that, remember that if I start with a set x, then the closure of x consists of the things that I can add to x without increasing the rank. So if that's true, then you can imagine that the rank of the closure is the same as the rank of x. Proof? Well, for each element of the closure, it is true that adding it doesn't increase rank. That's by definition of closure. Okay. And then remember that I proved a lemma for you last time, which said precisely what happened in this situation. It said if you take a set and adding every individual element to x doesn't increase rank, that implies that adding the whole set to X doesn't increase rank. This is a lemma from last time. So my lemma from last time. If this is true adding one X at a time, that means you can add them all at a time and get the same answer. But remember that, actually I haven't proved this to you, but this is pretty obvious that the closure of X is, contains X. And therefore the X union the closure is just the closure. So there it is. Rank of the closure equals the rank of the set. These are two useful lemmas that we're going to apply today. Any questions about them? Okay, so what I want to show you today now is that matroids do satisfy these closure axioms. Satisfy the four closure axioms that I stated last time, and I'm going to state it now. So first axiom, I think it's just that X is contained in the closure of X. Again, this is clear because the closure is the things that you can add to X without increasing rank. So if you add something that's already in X to X, you don't increase the rank. This is pretty clear. So let me this one is clear. What does the second one say? The second one, it talks about inclusion. It says that if X is contained in Y, then the closure of X is contained in.
Wait, is the actual definition of closure just what we said here? The things that don't increase the.
Let me write that down explicitly for you.
Yeah.
So the closure of X consists of the elements such that the rank of X union X equals the rank of X. So they are the little X's that you can add to big X without increasing its rank. Definition. So let's go ahead and prove the closure axiom 2. Seems pretty clear, but this actually does require a proof. So the usual thing, if you want to show that something is a subset of something, then you take an element in the first one, and you want to prove that it's in the second. Okay. So take an element in the closure of X. By definition, that means that the rank of X union X is the rank of X. Okay. Now, what I'm going to do is take a basis of X. Because B is the basis of X, and X union X has the same rank as X. That means that B is also a basis for X union X. Is this independent in X? X union X and it has the right size for it to be a basis.
Okay.
Now I want to go to Y. And so the idea is that I'm going to take this basis and extend it to a basis of Y. Let me point out something right now, which is that in fact B union X is dependent. Why is that? Because B is a basis, so everything bigger than B has to be, everything bigger than B and inside X union X has to be dependent. So B union X is dependent. Okay, so B is a basis of X union X, and I know that X union X is contained in Y union X. And so I can take my basis of X union X and extend it to a basis of Y union X. Extend B, which is a basis of X union X, to a basis C of Y union X. How do I know that I can do this? Because we know that when I restrict to Y union X, I still have a matroid. B is an independent set inside Y union X, and every independent set can be extended to a basis. So I extended B to a basis C of Y union X. So now I want to claim that C does not contain X. Why does C not contain X? Because C contains B, and if it were to contain X, then it would contain B union X, which would be dependent. It would contain B union X, which is dependent. So if C is a basis of Y union X, and it doesn't contain X, then I'm going to say this. I'm going to say that also, therefore, C is contained in Y, because it's a subset of Y union X that doesn't contain X. C is contained in Y, it's independent, and therefore the size of C is less than or equal to the rank of Y. So what happens? C is a basis of Y union X, and so the size of C is the rank of Y union X. So what I just showed is that the rank of Y union X is smaller than the rank of Y. But we know that rank is supposed to respect order. This is axiom 2 maybe. By the second axiom of rank, we know that rank is supposed to preserve order. So because Y is contained in Y union X, the rank of Y should be less than the rank of Y union X. So I have the two opposite inequalities, which means that actually I have equality. And what this equality means is exactly that X is in the closure of Y. So in one sentence, what I did is come over here and notice that B is both the basis of X and X union X, and then extend to a C that is the basis of Y and Y union X. And that's what shows that Y and Y union X have the same rank. questions about the argument? Okay, so that's good. Closure also preserves order. So if X is contained in Y, then the closure of X is contained in the closure of Y. The third axiom is that the closure of X is the closure of X. Remember I told you the way to think about this is if you start with X and you close it, it's already closed. So if you close it again, you're not going to do it. This is the right way to think about what this axiom says. But it requires proof again. To show that closure of the closure is the closure. Now we certainly know that one direction is true. I mean, we want to show these two things are equal, so we're going to show one inclusion, and then we're going to show the other inclusion. And we certainly know one direction because X is contained in the closure of X by axiom 1, and axiom 2 says, we already proved axiom 2, which
closure of X is contained in the closure of the closure of X.
Exactly.
That's what you're saying.
I can take closures on both sides. And
Right.
That's, yeah.
so this is true by the first axiom, and then by the second axiom I can take closure on both sides and get the easy inclusion. For the other inclusion, what I have to do is the usual thing. So I want to show this other inclusion. So let me just take an element of the closure of the closure of X. And I want to show to you that this set is actually an element of the closure of X. So what does it mean to be in the closure of the closure of X? Well, X is in the closure of something if adding it doesn't increase the rank. So adding little x to the closure of X doesn't increase
Closure of closure? What?
We're just
Doesn't
letting the
increase
inner
the rank.
closures.
Oh, the
that be
closure
the-
itself.
right.
Okay, got it.
Did I make anything?
No, okay, you're fine.
So this is just by definition, right? X is in this closure means that the rank of this guy, I mean, so I'm thinking of this guy as a Y, let's say.
Yeah.
So X is in the closure of Y if and only if the rank of Y union X is equal to 0. Okay, now what do I want to say? What I want to say is this. Notice that.
Can't you just say that that's the rank of X?
Yes, I mean using this. By the lemma.
So the lemma, this is the rank of X. Right. So now what I want to say is this. I want to say that the closure of X union X contains, well, the closure of X contains X. This contains X union X. And X union X contains X. But now, I just showed to you that this guy and this guy have the same rank. The rank of the guy on the left is equal to the rank of the guy on the right. And therefore this guy is stuck in between and has to have the same rank as well. Because this guy is stuck between two things with the same rank, that means that it has the same rank. The rank of X union X is equal to the rank of X. And this precisely means that X is in the closure of big X. Which shows my inclusion, my opposite inclusion. Good. So that means that closure does satisfy this third property. other closures. The axiom 4 says, see what letters I used last time, I said, for all x and little x, I said. So if big X is a subset, little x is an element. So I said, if you have an element y which is in the closure, it's not in the closure of big X, and it is in the closure, when you add little x, then that tells you that you can change the roles of x and y. Let's say that x is in the closure of x union. We're used to having exchange axioms in matrix theory, and this is the exchange axiom that says that if you're in this situation, then you can change the roles of x and y. Let me prove to you that this axiom holds. So axiom 4. I'm supposed to take y, which is not in the closure of x, but it is in the closure of x union x. Let's see what these things mean. What does it mean for y to be in the closure of x union x? It means that when I add little y to x union x, I don't decrease the rank. What does it mean for y to be in the closure of x? It means that when I add little y to x, I do change the rank. But if I do change the rank, then by the lemma that I just erased, when you add one element to x, you can only increase the rank by 1. So the rank of x union y is equal to the rank of x plus 1. So now what I'm going to do is this. The rank of x union little x union little y is equal to the rank of x union x. I showed that. Now, again by the lemma, I know that the rank of x union x is either rank of x or rank of x plus 1. So the biggest that it can be is the rank of x plus 1. But we know that the rank of x plus 1 is the rank of x union y. So what I just showed is that the rank of x union y is smaller than or equal to the rank of x union y. But again, by the fact that rank increases with the set, I have the opposite inequality. So if I have one inequality and I have the opposite inequality, that means that the rank of x union little y is equal to the rank of x union little y. And if you look at this, what it says is that when you added x to x union y, you didn't change the rank. So what this means is exactly what I wanted to do. The little x is in the closure of big X union y. That's my proof of closure axiom number 4. Questions? characterize matrix. So a closure operator, let E be a finite set. Closure operator that assigns to each set the closure of it, or rather an operator is the closure operator of a matrix if and only if it satisfies these four properties. Satisfies for properties 1 up to 4. Which is going to allow us to think of matroids as closures. Yet another point of view for matroids. And as usual, I showed you one direction and I'm only going to hint at how to get the other direction. So one direction is clear. If you have a matroid, then you do have these properties. We just did this. For the opposite direction, the question is, if I give you a closure operator that satisfies these, then why is it the closure operator of a matrix? Given the closure, how do you recover the matrix from it? Well, what you have to do is tell me, in terms of closure, what does it mean for a set to be independent? So, let's say that a set is independent if and only if what?
Closure is itself.
So when is a set independent? But what it means is that there are no internal relationships inside I.
Yeah.
In other words, no one element of I depends on the other ones.
So
So what I'm saying is that for each x in I, this element x better not depend on the other ones.
so it's not in the closure of I minus x.
X is not in the closure of the other ones. So you define this and then you have to check one, that this is a matrix. So you do that by checking that this definition of independence satisfies your 3 independence axioms of a matrix. And the second thing you show is that this matrix has the closure relation that you want it to have. The closure operator of this matrix is the one that you started. And again, I'm going to omit the details so you can either work this out yourselves or find it in option form. And of course, the proofs are very similar to what I've done. Details. The point that I want you to take of this discussion is that this really is a complete way of thinking about matrix and a very useful one at that. In other words, I said yesterday is that you can think of a matroid as a closure operator that satisfies that exchange axiom. And really that is pretty much a definition of a matroid.
To think about, I mean, maybe I shouldn't ask this yet because I haven't thought about it enough. To think about it this way depends on having a rank function already. So in each of the, like when we started with the independent sets, or I guess with the bases, we still had to have the notion of independence. So we didn't have to have the axioms of independence, we had to have the notion of independence. So somehow or another, this doesn't stand separate from the rank.
Well, it does kind of imply a rank function, though, right?
Yeah, I mean, the point is that we have these different notions so far.
Mm-hmm.
So we have the independence notion, we have the basis notion, we have the circuit notion, we have the rank notion, we have the closure notion. So these are already 5 different ways of thinking about a matroid. Each one of them stands on its own. And you can define a matroid by saying, for example, here it is. Here's my definition of a matroid.
So that's going to...
I could have started the class on the first day saying, a matroid is a set with a closure operator that satisfies this.
But to define the closure operator, you need the rank function already.
No, to define
No.
the closure,
To define the
we
closure
use
itself.
in a matroid when we already had rank. We
use
use
the
that.
Right.
But this is going to give you a rank function.
Right.
So the point is, and
Yeah.
I mean, I haven't done it because imagine this: we have 5 different notions of matroids,
So
and from each one you can recover one of the other ones. So there's 20 problems here. 5 choose 2 is 10. 10 problems here. No, 5. No, there's 20 problems.
It's a complete
It's
graph
either-
once.
either way.
It's K5 or
There's
something.
20 problems, which is given one notion, closure.
Right.
How do you define another notion? Rank. For example,
Mhm.
I am stating here that just from the closure you can recover the matroid, and that means you can recover the rank function. How do you do it? Well, it takes some work. So you start with the closure, then I showed you how to get the independence. Then from independence we saw how to get the bases. Then from the bases we saw how to get so on.
Right.
And actually, now that we are starting to learn all these different notions, I'm going to offer to you guys that there's a dictionary actually which goes from each notion to every other one. So if you have there's because you can really do this. And for example, if I give you the closure, then you can say independent set means this. So you can say rank means, and there is a dictionary that spells this out for you, so you don't have to do it every time. Because the point is that you do want to use these different points of view, but you don't want to have to do all the work. The point is that we already know that these are all equivalent, so you can feel free to use any one of them at any point in time. Like you have 5 different machines that are logically equivalent, but somehow psychologically they're pretty different from each other. I'm sure you guys are happy with different notions, so maybe James prefers, I don't know, what do you prefer?
I'm liking closure these days.
Nice closure. Kim, what do you prefer?
I'm still back with independence or basis.
I mean, different people are going to like different notions. When I first learned about this, I loved rank for some reason. So the first matroid theorems that I proved were all about rank functions. The proofs were all about rank functions, but maybe you would have proved them using bases, and you would have proved them using closure. And these are all independent points of view that might be better for you psychologically, but they're all logically equivalent. So far we have 5, but there's more. But here's one. So closure is 1.
Great.
Now, okay. Yeah.
Good. Cool. One of the final projects would be to write that dictionary.
Yeah, sure. So
Just every.
I don't know that anybody actually wants to do this. I mean, sure. Project. Rewrite or check or whatever. Rewrite, reprove, check, however you want to say it. The dictionary.
So you mean every pair show every pair if and only if it.
Independent sets,
But I mean,
bases.
that's not how you normally prove a bunch of things are equivalent, though, right?
They usually do a loop.
Yeah,
Mhm.
which is what we've essentially been doing.
Yeah.
Right.
Or we've been showing they're all.
They give you practice doing like
Yeah.
trying to go to.
So it is very good practice to
Yeah.
to do this. And again, you start working on matrix theory, you have one favorite notion, but soon you start realizing what the advantages are. By now, I'll tell you maybe I'll use 3 different notions. Okay, so I still have 4 more to go.
Well, I get the idea that we can define matroids in all those different ways, but how does that relate to a dictionary? What does that have to do with a dictionary?
Well, let me put it this way. So how is this a dictionary? Because
If you have this closure, then your rank should be this, and your circuits should be those, that kind of thing.
yeah, so for example, I don't know, maybe you can think of the independence language. So the words in the independence language are the independence sets. The words in the circuit language are the circuits.
If you know what the independent sets are, how can you find what the circuits are?
I'm sorry?
So if you know what the independent sets are, how can you describe what the circuits are?
Exactly. So the independence circuit language teaches you how to say independent concepts in circuit language.
Sounds more like a thesaurus.
Well, let me show you how it's a little bit more of a dictionary. So I haven't really expanded on this. But for example, how did I define duality? I defined duality in basics language. I said, if you give me a matroid with these bases, then I'm going to define a dual, and these are the bases. But the way I learned how to define duals, it was in the rank language. It told me if this is the rank function of a matroid, then I define a second rank function. And this happens to be the rank function of some other matroid which we're going to call a dual. And so that would be an entry in the dictionary, is translate dual from the basis language to the rank language.
Yeah, it'd be a real smart dictionary though, because it's not giving you a word for a word. It's giving you like an idea for an idea, sort of.
Yeah, so maybe the dictionary isn't exactly the only part of the project is to figure out what this is. I don't think it's exactly a thesaurus either, but that might be more accurate.
What do you call something that tells you how to say things in a bunch of languages?
The translator.
Grammar checker. I don't know. Anyway, part of the project you would have to figure out what your project is called. Actually, the next thing I wanted to give you is another project, which I think is very neat. Which is that I'm going to I'm going to change axiom 4. I'm going to change axiom 4 and I'm going to consider a different axiom, 4 prime, which is not equivalent to 4. I want this to be clear to you. It's not equivalent to 4. It's a different axiom, and it says this. It says so it's exactly the same axiom, except the conclusion is the opposite. So the idea is this, that if you take the axioms 1, 2, and 3, then this defines what a closure is. If you have a closure and you have the 4th axiom, then this defines a matrix. And matrix, as I hope you understand by now, are some abstraction of a combinatorial abstraction of the idea of independence. Combinatorial abstraction of the notion of independence. Well, it turns out that if you consider the closures I call this the exchange axiom, which said that in 4 over there, I can exchange x and y. So now if instead of the exchange axiom, I impose the opposite axiom, which one might call the anti-exchange axiom. Anti-exchange because it says that you cannot exchange x and y. Okay? If x satisfies the condition, sorry, if y satisfies the condition, then x doesn't. Then you get a whole other theory, which is the theory of convex geometries. And the theory of convex geometries is a combinatorial abstraction, you can guess, of the notion of convexity. So if this is true, then probably you can think of one notion of closure that satisfies anti-exchange, which is convex Hall. So if you have if you have a bunch of a collection of vectors, you take let's say you take a bunch of points over here. What is the convex Hall of 1, 2, and 5?
Connect it all.
The convex Hall.
You mean in some kind of discrete sense?
On the
By those
board.
points?
Yeah, so
So you're going to get,
what would be the discrete version of the convex Hall of 1, 2, and 5?
you're going to get 1, 2, 5, 6, and 7, probably.
So
Yeah.
regularly a convex Hall is just the smallest convex body containing 1, 2, and 5.
Federico, are you saying a convex Hall? I just haven't heard this before. H-A-L, what?
H-U-L-L.
Okay, okay, thanks.
Convex Hall. Actually, thanks for asking that, and let me also translate that to Spanish because I'm sure they're wondering what I'm saying. Envolvente. So, generally, convex Hall, the convex Hall of 1, 2, and 5 is basically the smallest convex thing that contains it. So here it is. But if I ask you to take a subset of these points and call that the convex Hall of 1, 2, and 5, then you would pick 1, 2, 5, 6, 7, because 6 and 7 are the ones that are inside the triangle 1, 2, 5. Okay. So what I'm claiming is that this notion of convex Hall satisfies the anti-exchange axiom, and it defines the convex geometry. And just like for matroids, there are several examples of dependence notions that are matroids. It's also true for convex geometries that there are several notions of convexity in mathematics that obey the same axioms, and these are the axioms of convex geometry. And so a project would be to read about that and see that actually there's a lot in common. And there's, of course, several differences too. So the project would be to read about this, learn about this. Any questions about this before I move on? Convexity in general is a notion of between
So can we just talk real quick, like an example in this picture of how it works out? So if you have, say, 8, if you add an 8 into your set, it's not in there.
So let's talk, for example, about.
Just choose an extra point and choose an X and a Y that.
So for example,
So
let's
check
see an example of
that.
anti-exchange here.
Yeah, that's what I
Right.
mean. Yeah,
So add 4 in.
sure.
So, well, let me put it this way. Let's say that 7 is in the convex hull of 1, 2, and 5,
Yeah.
but it is not in the convex hull of
1, 2.
1 and 2.
Sure.
Mhm.
Yeah.
So, without looking at this picture, without looking at that specific configuration, I wanted to try to understand why the conclusion of anti-exchange holds, which is that. So let me write it in the same order as I wrote it there,
Right.
so that it's not confusing. So 7 is not in the convex hull of 1 and 2. 7 is in the convex hull of 1, 2, and 5. And the question is, can I exchange 5 and 7?
Convex hull of 1 and 2 is just the edge, 1, 2.
Convex hull of 1 and 2 is just
1, 2.
this edge.
Yeah.
Mhm.
Or in this
The
sense,
thing
just
between 1 and 2.
just the
Yep.
just 1 and 2 in this setting.
So
Right.
if 7 is between 1, 5, and 2, then 5 must be outside of 1, 2, and 7. So
So the conclusion of anti-exchange is that 5 should not be in the convex hull of 1, 2, and 7.
Mhm.
And let's try to imagine, without looking at this picture, without looking at this specific configuration, why is this true? 7 is not in the convex hull of 1 and 2, so that means here's 1, here's 2, here's the convex hull, and 7 is not in there, so 7 is outside. 7 is inside the convex hull of 1, 2, and 5, so no matter where I put 5 in here, what this is saying is that 7 is inside that triangle. The conclusion is that 5 is not in the convex hull of 1, 2, and 7. Well, that's clear because if 7 is inside the triangle 1, 2, 5, then 5 cannot be inside the triangle 1, 2, 7. So this is how anti-exchange plays out in this example. And with a little bit of work, you can formalize the idea, which is exactly this. This is how you show that the usual notion of convexity for a configuration of points satisfies anti-exchange. Any other questions about it?
In this idea of convex geometries, do we actually have an idea of independence of a certain number of points? Like, I mean, when we talk about matroids, we have a sense of independence and spaces and all these. Is there an equivalent of those in convex geometries?
Right, so the question is, so for matroids, maybe the key thing, at least the way we started this class, was independent sets. So in convex geometries, what do you think is the key notion?
Convex sets.
Convex sets.
What
So
about
just like here, everything talks about independence. Here, everything talks about convexity. And so, one of the first things you would do in your convex geometries is see what properties convex sets have. So then you get these axioms of convex sets, and so on.
what about affine independence though? We haven't talked about that really here, but it's really just linear independence, right?
Affine independence is actually a matroid independence.
Yeah. It's pretty much linear independence.
Affine independence is basically the same thing as linear independence. I think those of you who took the Polytopes course last semester know what this means. The other ones probably don't, but it's basically the same thing, which is why I haven't talked about it too much, because it doesn't add very much and it might confuse people when it's unnecessary. Okay, it's a good point to stop.
What?
Movie fan?
Even though I know they're all just going to sit there and space out and not pay attention if they ever
So
ask.
what are you doing this?
Huh?
What were you saying?
Oh, I'm deriving the quadratic formula.
Why not have them do it?
I mean, I'll have them do stuff, but I don't really want to have them do that.
I mean, no, like what I mean by
I don't teach completing the square at all.
I don't
But
remember
so,
the name of the
so what I'm saying is,
Oh,
if you
23?
a way to do it
There's one called 23.
is imagine the steps you're going to do.
Yeah.
You do the steps that you need to do,
Did you see it?
and leave blanks in between, and then wander around the room and have them
Yeah.
try and find those blanks. It at least requires them to then at least think about why you did what you did.
That's true.
Right? And sometimes if you do that with sort of not exactly in a two-column proof way, but if you know if you do like
You do a step and you write a reason.
you're right, but you don't have to do that. But you can do like, okay, you do a step, and then you say, okay, and you say the reason,
Yeah.
but you leave a space and you say, okay, you guys write down why that's true. Now you do another step and have them write down the reason, and then you say, okay, now I'm going to have you figure out what's the next step. I'm going to give you a reason that would be true. You know, so you sort of start them off and set them up, and then say, you guys can figure this out. You're capable of it. Give it a shot.
Yeah.
At least they won't just watch you do it.
Yeah, I was going to have them use it after I gave it to them.
Yeah. But they probably all know it.
Yeah,
I mean, not know it, but they've all seen
They've
it before.
seen it.
Exactly. Exactly.
Yeah. I just don't like writing magical formulas like the book likes to do.
Yeah, I don't either. That's what I'm saying. But if I'm gonna bother to do
Yeah,
it in
that's
person,
true. That's true.
then I'd like them to see.
Like the vertex, like where the vertex of a standard form
Right.
parabola is, they just put this magic box.
Right.
Like it's at minus b over 2a and f of that.
Right.
It's not that. Like I could
It's
have
not
gave
that
them a
hard.
homework to just prove that.
Sure.
I mean, tell them, look at take the vertex form, expand it out. Now match up your.
Right.
Your
Or
guys.
take the roots. Right.
Oh, if you don't have the roots yet.
Right.
Where like the vertex comes before the
Yeah,
roots.
yeah, yeah.
But still, you just take
But-
the vertex form, you say a times x minus a squared plus a, then set that equal to ax squared plus bx plus c, and
Find
solve
it.
for h.
Exactly. Yeah.
Oh, you are?
Yeah.